Scientists just discovered a shadow inside our own solar system, about 25,000 kilometers out, roughly 166 AU from the Sun, where sunlight still exists, but it can't do what sunlight is supposed to do anymore. But the contradiction gets sharper. A probe sits out there anyway, and it still talks to Earth like it refuses to admit the Sun can't reach it. And it's dying faster than the mission plan can comfortably survive. However, it keeps whispering across about 23 hours of one-way light time, which means every message you send becomes a promise you can't immediately check. Every bit that reaches the deep space network comes from a machine running on the last crumbs of internal heat, not solar power, but that also means every new data point might be the last clean data point it ever sends. So why does a place this far from the Sun suddenly look like it has an edge instead of a smooth fade? According to the inverse square law, sunlight never turns off, but distance dilutes it so brutally that engineering treats still shining and still useful as totally different realities. At 166 AU, sunlight drops to about 127,556 of Earth's intensity, so weak that solar panels become decorative glass. However, the probe detects a drop in the Sun's scattered glow that feels sharper than distance alone. That's like trying to warm your hands with a stadium floodlight, but the floodlight sits in another city, and the air between you acts like a weird lens you can't see. So what creates a crisp, dimming line in a place that should only blur? For 6 months, a navigation and plasma team treats the anomaly like an embarrassment they can delete with a checkbox, but every simple answer collapses. They blame sensor drift, however, the dip stays locked to a direction in the sky instead of slowly sliding with time. They blame a tracking artifact, but the pattern repeats across separate DSN passes and different geometries, including links that lean on a 70-meter dish built for exactly this kind of impossibly faint whisper. Then they look at the data one last time, and the dip sharpens into an edge, which is the one shape you do not expect from emptiness. So what draws an edge in open space? The discovery lands hard. The probe skims a thin boundary layer, where neutral gas and dust scatter sunlight differently. So the heliosphere stops behaving like a smooth cartoon bubble and starts behaving like a structured object with seams. 3 details lock it in, but each detail also feels like a trap. The dip aligns with the incoming interstellar wind direction. The transition steepens across only about 0.3 AU, which is razor thin on this scale. And a dust counter logs a sudden rise in impacts right when the edge appears, but correlation loves to lie when you want answers. Here's the crazy part. Along that wedge, the glow drops by almost 30%, but the background stars look normal. So the universe doesn't dim, only this. Specific sunlight scatter does. How do you erase sunlight's fingerprint without touching the starlight behind it? But here's what breaks them. The edge moves. It ripples in sync with pressure pulses that ride outward on the solar wind, which means the heliosphere acts less like a glass bubble and more like a breathing membrane. However, breathing implies flexing, and flexing implies weak points, and weak points imply leaks. One fundamental assumption starts wobbling under everyone's feet. The Sun's shield against cosmic rays stays basically stable and predictable. If the shield breathes, what slips through when it exhales? That question stops feeling poetic the moment you translate it into hardware and flesh. First, crude missions outside Earth's magnetosphere take radiation swings that don't respect schedules, but schedules still demand launch windows and mission durations, like the universe signs contracts. Second, deep space navigation gets nastier because changing plasma bends radio phases like heat haze bends light. However, the probe still forces data through at around 160 bits per second, like a stubborn heartbeat you refuse to stop listening for. Third, future interstellar missions fail on power unless they carry long-life generators, because at 166 AU, even sunlit hardware trends toward an equilibrium near 22 K, about 251 degrees C, and sunlight stops being a tool and becomes a faint aesthetic. If sunlight becomes useless that far out, What other intuitive truths die with it? Not everyone agrees, and the argument turns into a brawl over whether the edge lives in space or inside the instrument. Dr. Celeste Rahman at the fictional Caldera Institute says, "A shadow that sharp doesn't happen without a trick. Either the universe cheats or your detector does. But the team keeps cross-checking, and independent channels keep matching, and the detector did it escape hatch starts closing, like a door you suddenly need open. If the instrument stays honest, what structure out there stays sharp enough to cast an edge? One signal refuses to fit even the boundary story, and it arrives like a knock you can't unhear." At exactly 02:17:43 UTC during a downlink pass, the carrier grows a tiny sideband tick, then the plasma count jumps, then everything settles like nothing happens. The tick clusters near the edge of the shadow wedge, but clustering can seduce you into patterns that aren't real. So the team tags it against pointing, station handoffs, thermal cycles, every operational excuse that could fake a coincidence. However, the tick survives those tags often enough to stay scary. What hits a spacecraft out there? Dust? A filament of charged plasma? Or something that only exists where the sun's influence thins? Now the power problem stops being background tension and becomes the blade at the throat of the whole story. The probe runs on a radioisotope generator, not solar panels, but decay squeezes the mission. Like a vice you can't loosen. The spacecraft budgets something like 200 watts for everything it does, but heaters, radios, and instruments fight for that power like starving wolves. Engineers shut off one subsystem to save another. However, every shutdown changes temperatures, noise floors, and timing, which can create phantom edges in faint signals if you aren't careful. So the team faces a cruel logic test. How do you prove the universe changes when your own spacecraft changes every time you save it? The communication itself feels like magic right up until you stare at the numbers and realize it's math doing violence to hope. The probe transmits at about 23 watts, less than a small light bulb, but Earth still hears it because the DSN turns whispers into evidence with giant dishes and ruthless signal processing. However, the radio wave doesn't travel through nothing. It threads plasma that bends phase and subtly distorts the path, so the same medium that threatens your data also reveals the boundary's structure. When the wedge edge lines up with nastier radio conditions, the coincidence looks delicious and dangerous at the same time. Does the boundary create the radio distortion, or does radio distortion fake the boundary? Here's the scale moment that makes the edge feel real instead of academic. At 166 AU, the sun still shines, but it can't keep a spacecraft warm without internal heat. That's like leaving a running car engine in Antarctica, but the Antarctica sits 25 billion kilometers away, and the cold sits near 22K, so even daylight feels like night to your hardware. If a thin layer changes scattering there, the layer behaves like a cosmic frosted window, bright from one angle, dark from another. But why does the frost form a crisp edge instead of a smooth blur? 3 culprits step forward, and each one sounds plausible until you demand it explain the sharpness without cheating. Culprit 1. Dust. Dust scatters light, but dust usually smears gradually. However, a dust sheet aligned with magnetic fields can behave more like a plane than a cloud. Culprit 2. A magnetic seam. A seam can stay sharp, but it has to hold its shape while the solar wind pushes it like surf. Culprit 3. Charge exchange. It paints energetic neutral atoms in patterns you can map, but a geometry flip has to produce that 30% drop without dimming starlight, which feels like threading a needle in the dark. So which culprit predicts the 0.3 AU transition width without inventing new physics? Then the tick returns and refuses to act like random dust. Dust hits should feel scattered, but the tick clusters near the wedge edge like it reads the map. However, the team knows how humans fool themselves, so they search for operational rhythms that could imitate clustering, and they keep finding nothing clean enough to blame. When the tick survives the excuses, it starts looking physical, and that turns the wedge edge into a place you can almost touch, which is a terrifying thought in interstellar adjacent space. If something physical lives at the edge, what shape does it take? A sheet, a filament, or a shock that behaves like a wall? The story turns human now. because one command can kill the mission. Mission Control stares at a choice that looks simple in a spreadsheet and violent in reality. Boost transmitter margin or keep the key faint glow instrument alive. If they boost the radio, they lose sensitivity where the shadow lives. If they keep the sensor, they risk losing the link forever. But here's the crazy part. That decision also becomes an experiment, because instrument state changes should not move a boundary in space. So what single test separates instrument illusion from space structure with one flip? They run the trap. Same pointing, same DSN geometry, same timing, different internal spacecraft states. If the edge shifts with internal state, the instrument owns the shadow. However, if the edge stays fixed on the sky, space owns it. The edge stays fixed, and that result doesn't end the argument. It sharpens it, because now the universe carries the burden of explaining the shape. If space owns the edge, what mechanism keeps it stable while the heliosphere breathes? Now 2026 starts to matter because the next wave of precision forces the universe to stop hiding behind messy calibration. ESA's Plato, scheduled around 2026, pushes ultra-stable measurement disciplines so hard that whole communities steal its calibration habits for faint signal work. But improved calibration also acts like a lie detector. The edge either survives the cleaner math or evaporates instantly. And ESA's Hera, also on a mid-2020s timeline, turns a different boundary into a close-up lesson, reading the DART impact system like a scar you can measure. However, the deeper theme stays the same. Boundaries carry structure, and structure carries consequences. If calibration gets brutally better in 2026 and the shadow still holds its shape, what physical wall sits at the edge of the sun's domain? Poll time and pick one like you mean it. Which explanation survives a full year of scrutiny? A. Dust sheet, B. Magnetic seam, or C. Charge exchange geometry flip? Dust predicts gradual change, but the data shows a cliff. Magnetic seams predict sharpness, however they should drift as solar pressure pulses. Charge exchange predicts directionality, but it must match the 30% drop without collateral dimming. What measurement confirms one option and kills the other two in a single day? Now, the comment questions that matter most land like mission control dilemmas instead of casual prompts. Question 1. If you control one last pointing maneuver, do you aim the probe at the wedge edge to sharpen the boundary map, or do you aim away from it to hunt the source of the tick? Question 2. If you gain one extra year of life by shutting down a key instrument, do you sacrifice the mystery to extend the heartbeat, or do you burn power now to chase the truth while the transmitter still holds lock? Either choice feels wrong, but one choice might be the only reason the story ever gets an ending. Dr. Kenji Alvarez, a fictional heliophysics lead, says, if the sun casts a shadow this far out, then the solar system has an edge you can feel, and edges always hide something. But that line only matters if the edge keeps behaving like a place instead of a glitch, so the team pins the wedge on a sky coordinate and schedules the most dangerous plan. Skim the edge again and again until the tick either repeats predictably or vanishes forever. However, every skim costs power and time, and every lost watt steals tomorrow from the mission, which means Discovery now competes directly against survival. So comment your best theory and make it specific. Dust wall, magnetic seam, or charge exchange flip, and I'll pin the sharpest explanation, because the next round of 2026 grade precision either confirms a real boundary structure or exposes the cleanest illusion ever recorded. Subscribe for the 2026 results, because this story only exists as long as a dying probe can still whisper across 23 hours of darkness. And the moment the whisper stops, the edge becomes a rumor again. Next week, the black hole that's eating itself. But first, if this probe finally crosses the edge completely, does it find empty space, or the first hint that interstellar space pushes back?